Okay, so I'm going to move on to something that's going to seem like it's completely unrelated, and for about a half hour it's going to remain completely unrelated in my guess. But it ends up, I think it's good. So it ends up that these ideas of noise perturbation is essential for the proof of KKL. Really, the big tool is working with this noise operator. So the idea is as follows. I'm going to fix a function, pick a function, and pick an x somewhere in the Hamming cube. And I'm going to fix an epsilon as well, and I'm going to consider the following operator. At each point, I have, with probability 1 minus epsilon, I do nothing. And with probability epsilon, I look in a direction and I change. So that I basically am going to look at all n directions, starting at my point, and take a step in epsilon n of them on average. So I'm going to perturb each one and take a step on in that one. The other way to think about it is as follows. I take a string, x, x1, x2, x3, x4. And for each one, with probability 1 minus epsilon, I keep it the same. With probability epsilon, I re-roll it. So I consider an independent copy of xi on that guy. And the question that we're going to be interested in is, given a function f, and with what probability does this operation, on average, change my value? This is the idea of noise. The metaphor they give a lot when you sort of think about this in social choice theory is, suppose you had an election and an epsilon fraction of the votes are lost. And you just sort of say, okay, I'm just going to roll them at random. What's the probability that I actually change the outcome of the election based on this mistake? And of course, what we're interested in is what happens when epsilon is small. Now, if n is fixed and epsilon is going to 0, we know nothing's going to change, right? We have a fixed number of outcomes. And the noise goes to 0. We know obviously, as epsilon goes to 0, by continuity and the fact that everything is uniform on a finite set, we really know that the limit of that operation for a fixed n as epsilon goes to 0 is not going to change anything. But uniformity in n is far from guaranteed. So the idea of a noise-sensitive function is one such that if you have a sequence of functions now on more and more bits, consider, let's say, percolation on larger and larger squares. You want to cross a square from left to right, lambda n squared, and n gets larger and larger. Suppose I take a percolation configuration and see, oh, this one crosses. And then I randomize an epsilon of the edges. As n goes, if I fix epsilon and send n to infinity, and then send epsilon to 0, am I going to cross if I knew that I crossed in the beginning, or am I not going to cross? And what are the probability event? Is it going to be completely randomized? Is it going to be somewhere in the middle? So this is a question of noise sensitivity, and this is sort of what these kind of operators are there for. In addition, as I mentioned, this is a random walk operator on the Hamming cube. And as such, it plays the roles of a heat kernel. And what do heat kernels do to function? They regularize them. They really, genuinely make them much, much nicer. So at least in Fourier world. So the fact that this allows us to control some information about the Fourier mode is going to be an essential tool, and really the thing that allows us to prove KKL and all these other, and the other major theorem, which I haven't stated yet, the noise sensitivity theorem, about the spectrums of Boolean functions. So let's begin. So the experiment is as follows. We fix epsilon, pick x uniformly at random. Actually, just fix x. Now, for each xi, keep it with probability 1 minus epsilon, randomize it with probability epsilon. And then once I get a new string, sample f at this new value. So what this does is this gives me an operator on L2, a noise operator on L2. That is, for a fixed epsilon, I'm going to get a random variable, which is an f of x at a different value. And of course, since I want it to be a deterministic function, I'm going to take expectations. This defines a function L2 and omega that somehow measures the epsilon noise of f. So let's define this formally. Probability wrong. So I give you a vector x, and n rho is going to give me the exact same value xi with probability rho, and a random bit that's uncorrelated with probability 1 minus rho. Okay? This is exactly that operator. I said go bit by bit and do this independently for each bit, and randomize a 1 minus rho factor. I just want to make sure I did this right. Yeah, you want n1. So notice that n1 of x is just x, and n0 of x is completely independent of x. I define T rho, the noise perturbation of f by rho, to be exactly the expected value of f of y, where y is distributed as n rho of x. So it's the slight perturbation of x. Okay, all of this sounds completely opaque. But the reason we do this is because given this definition and given this particular normalization, there is a very, very nice Fourier expansion for T of rho of x. Only thing we do is simply multiply the usual Fourier expansion by rho to the s. Now before we prove this, the intuition behind here is key, because what does this noise operator do? It punishes large spectral sets. In the sense that sort of the larger the set, the larger the dependence, the more the noise completely kills it off. And what this tells us is that having large Fourier sets makes you very, very sensitive to these small perturbations. It also makes it clear that the intuition that if you think of noise sensitivity as keeping your value up into noise, the most noise that's noise stability. Noise stability is keeping your value, and noise sensitivity is losing your value. The most noise sensitive function is parity. Right? If I have a guy that's supported completely on a set of size n, this gets me a rho to the n. That makes perfect sense. If each particular bit can change everything, it's sufficient for you to not randomize one bit for you to not know at all whether you were even or odd the first time, because one guy can change everything. So the fact that sort of gives us another way of thinking, what do these Fourier coefficients actually represent? So again, T rho is linear. So it's efficient to analyze how it acts on the basis elements. Now, suppose I look at xs, which is not evaluated at x, but at the random variable n rho. So if I randomize any of the bits in S, then the expected value of this is going to be 0, right? Because that one bit is now independent, and I take an expectation over a random bit, and I get 0. So I guess this is equally likely to be plus or minus 1 if any bit is randomized. And if, of course, I miss every single bit, that is, I don't randomize the first one, the second one, I just get chi s of x back. So therefore, and that's equal to 0 in this case, because every outcome is equally likely. And we just need to come up with the probability of none of the bits randomized, but that's an independent event, and the probability of that is rho to the size of s, and we get out chi s of x. So to measure noise sensitivity, we want to say, okay, I give you f at a particular point, and then I randomize it, and I get a possibly equal, possibly different value, some random thing, and I want to average over all possibilities, so that if these match, if f and t rho of f are completely equivalent, this would be 1. If they're completely orthogonal, it will be 0. So the correct thing to look at is this correlation, which by our Fourier expansion is just equal excuse me. Written in this form, you can also consider this. Is this clear? Just because we just take the inner product of this with the normal Fourier expansion. So that's why it's squared, while this is kept around. This is, of course, exactly the expected value of rho to the power of the size of that spectral sample we defined before. So as I mentioned before, if I fix n, so if f of x, if s is fixed, and rho is sent up to 1, but this limit is not necessarily uniform. So I'm going to define, this is not necessarily the standard definition, but it's equivalent to that standard definition, the noise sensitivity of a function as follows. Definition. Boolean functions. The noise sensitivity at epsilon n I'm going to call it 1 minus this, where I have an epsilon noise, so rho is 1 minus epsilon. Right? We want the probability of changing to be small, not large. So it's a bit of an awkward, but I wanted the rho to be rho, so I had to sort of switch a few things. Notice that if these are perfectly equal, then we get 0. So this being 0 means the guys are totally together. If these are totally orthogonal, that is, this and this give you no information. They're zeroly correlated. This is equal to 1. I'll do it up here. We say that the sequence Fn is noise stable if the limit in epsilon going to 0 notice that we take the limit in n first and then in epsilon. So we fix the noise, let the number of functions we have go to infinity, and then take epsilon. Sequence noise sensitive is equal to 1. That is, any noise whatsoever makes these decouple completely. So as we mentioned before, parity is noise sensitive. Because if I just consider this product, I get 1 minus epsilon to the n. And for any fixed epsilon set n to infinity, that's nothing, and we get this to be 1. Obviously, dictators, for example, noise stable. Because the probability of changing that guy's mind, it's an epsilon, you send epsilon to 0, you're not going to change that guy's mind. Now, it turns out that majority is also noise stable, which is good, right, for the notions of democracy and things like that. You don't want small errors to interrupt. Proving that fact actually requires a bit more work than we have done up until now, but it's very easy to show that stability is not noise sensitive. And why is that? That's exactly equivalent to that computation we did, the fact that we have a Fourier mass of 2 over pi at level 1. So if you think of it in terms of spectral sample, the probability that the spectral sample, is equal to is supported on a set of size 1 is 2 over pi. And therefore, when we look at this expectation, it's bounded below by 2 over pi times rho. So there is no way that that's going to 1. Sorry, is it below or above in this case? This is bounded below, so therefore this is bounded above because of the extra minus sign. So this is at most pi minus 2 over pi. And in fact, it goes all the way to 0 if we don't just look at the first level, but all the levels in between. But there is something awkward happening, because notice the following thing. Consider the derivative in epsilon. I guess this is a partial derivative. Using this formula and following all the minus signs, the fact that this is 1 minus epsilon, that should be 1 minus epsilon, not a rho, right? Because we're evaluating this at 1 minus epsilon. So the derivative at epsilon equals 0 is exactly the influence of a function. So if we have a sharp threshold, we're expecting that influence to go up to infinity, right? So what we're seeing here is that the noise sensitivity is, for any function with a sharp threshold, not differentiable at the origin when we take the limit in n. So what we're seeing here is, even if this function is continuous, at the origin, it definitely has an infinite derivative. And the question is basically, how good is that derivative? If that derivative is somehow sufficiently infinite to make it discontinuous at the limit, we get a noise-sensitive function. So in a way, noise sensitivity is sort of sharp threshold on crack. It's just a much stronger version of it that requires you not only to be not differentiable, but not continuous when we take that limit. And in fact, you'll see that for majority, as n goes to infinity. So we do see we have a non-differentiable thing, but it's still continuous. And the way to actually compute this might look mysterious. This is purely combinatorial argument of actually computing those higher expectations of what exactly needs to be equal, what exactly doesn't, and you just get binomial coefficients that, give you an actual explicit formula for ns of epsilon of n as n goes to infinity in terms of, I believe, an arcsine. Because, of course. There's no reason to guess that it's arcsine. It's just a matter of a discrete computation and Taylor series. So the other thing is that because of this representation, we can actually phrase noise sensitivity in terms of the spectral mass. And it's a bit intuitive, because if we look at this and we consider a sequence of functions, if we have any mass whatsoever, that even as n goes to infinity, let's say the probability that SF, that the size of the spectral sample is, let's say, 5, is a uniform constant, there is no way I'm going to be noise sensitive, right? Because this is going to be at least a constant, and therefore this is going to be at least, it's never going to go all the way to 1. So in order for this to work, I need to make sure that all my spectral mass is being sent off to infinity, or of course at 0. That's actually a complete characterization. In here. I have to always exclude the possibility of this being 0. Because remember, the empty set gives you the mean of a function. So it'd be sort of mean to ask for a function to have mean 0 in order for it to be noise sensitive. And that's in fact not what we do. Because you can tell from this formulation, if I pick the empty set, nothing happens. I don't get any contribution whatsoever. So as long as I don't pick up the mean, which could be anything, then I need the rest of the sample to go off to infinity almost surely. That is, the probability of it being between 1 and k needs to go to 0 as k goes to infinity. Similarly, if that random variable is tight, that is the probability of it being outside of any given compact set goes to 0, then we have noise stability. Again, by this exact same argument. You have some epsilon mass which is far away, and the rest is going to be bounded by a fixed power of 1 minus epsilon. Sending n to infinity it's completely uniform in n, and therefore once we send epsilon to 0, we just get 1. Would you guys actually like to see the proof of this, or because this is very much just manipulations as written here? I'm taking that resounding silence as no, we understand this perfectly. Thank you, Matan.
Yeah, so SFN is tight if there is a random finite set where S stays.
Yeah, so the to define this properly, is that for all epsilon positive, there exists a K such that and no dependence, not allowed to depend on n. So essentially, just all the mass, if I look at a large set, this K can be arbitrarily large, but it cannot depend on n. So we can't have, let's say, the mass at log n. That's not okay. But it can be at 1, 2, 3, 4, 500, 3 million, I don't care. It just needs to stop at a finite number.
Am I correct that there is actually something in between, noise stable and noise sensitive? Or?
So there are functions, actually, which are neither. So it's possible to have this limit be strictly between 0 and 1. They're completely and utterly fake, in the sense that you really have to work hard and sort of make things happen in unknowingly trivial ways to make it happen. But most functions are either, most interesting things are noise stable or noise sensitive. Okay. The next theory I'm going to state here is, in my personal opinion, black magic. There's really no other way to describe it. It's the completely insane statement which states that noise sensitivity, despite being a question of infinitely many norms, is completely characterized by the first one. That is, for Boolean functions, all you need to tell me, at least monotone Boolean functions, all you need to tell me is the first Fourier modes, that is, the influences, and I can already tell you whether the function is noise sensitive or not. This is really, if you think about this in terms of the overall L2 space, this could never be true, right? If in L2 space, if I tell you something at a particular spectrum, it tells me absolutely nothing about the rest of the spectrum, right? You can just span it. Even if we restrict to the L2 norm being fixed to 1, you can definitely make things happen in the first norm and then anything happen in the rest of them, so that you can make it so that, let's say, half the mass is at 1, and then the rest of the mass is going off to infinity. Very easy to do. Apparently, it's impossible to do while keeping the function Boolean. And somehow the fact that we exactly restrict them to be those two values, or two values in general, up to normalization, gets you some non-trivial information about how these Fourier spectra interact with one another that allow us to give these very, very strong characterizations. So this is.
Sorry, I understand the second part of the theorem, but not the first part.
The first one?
Yeah.
Oh, okay. So what we're saying is that SFN cannot have any mass between 1 and k. So it's very similar to this, in this you just say you put a 1 for all epsilon, for all k there exists an epsilon. For all k and epsilon there exists an n sufficiently large, such that the probability that this is between 1 and k is smaller than epsilon. So for all k, for all epsilon positive, there exists an n sufficiently large.
Why does that mean that the spectral sample concentrates at 0?
It might concentrate in 0. We don't know what happens at 0, right? So the issue here is the following triviality. We don't, whatever the 0 sample is, it doesn't really contribute anything to this contribution, right? Because the empty set guy is just the mean. It's a number. It's going to tell me so I can have a biased function that is, it's going to give me 1 3/2, like 3/4 of the time, and only -1/4, and only -1 with 1/4 of the time, excuse me. And still be noise sensitive, right? By just, let's say, I don't know, adding a constant and dividing by something to keep it Boolean. So we sort of don't want to worry about the 0 spectrum, because that just means a biased function. There's really nothing deep here. It's just that if this is equal to 0, we're not getting anything.
But doesn't it contribute, 1 times the probability of being 0.
I'm trying to see if you might be right that as I wrote it down, I might have been assuming mean 0. Usually, the way I cut a few corners, honestly. I cheated you guys. In the sense that usually the way noise sensitivity is phrased in the more careful way is that you take T rho and ask what's the probability that T rho differs from the mean. I looked at correlation because I thought this was sort of an easier way and gets you the formulas faster. So you might be right that I might have been cheating you guys and assumed mean 0 in some of this formulation. Let me just see.
I mean, for this theorem, I assume you meant something like that the mean was bounded. Because if you have like, you could come up with a bunch of functions that have like mean, like nearly 1. Like, that it's the constant function except that it has like a really high Fourier mode. And then, like from most
they correlate. You're right, this is incorrect. As stated, I assumed if I assume that and therefore this part, I can get rid of this as stated. Everything in this definition assumes that the mean is 0. Otherwise, I have to also subtract the mean to make things work. Thank you. I did something stupid. You're right. For the purposes of our discussion, imagine that the mean is exactly 0.
Okay, so in that case, the spectral sample is never 0?
Well, yes, because f hat of s is 0.
Okay, so it's never 0. Okay.
Thank you. So where was I? BKS. Yeah, I'm not going to have time to do that. Okay. So, noise sensitivity theorem of, this is done by Benjamin Nicolai and Schramm in, I believe, 98. And it states the following thing. So I have a sequence of functions. The number of bits they depend on doesn't necessarily have to be linear. It could be any function of mn going to infinity. So if this is, for example, consider percolation on a square of size n, you're going to have n squared bits. So it turns out that despite the fact that the condition is normally stated in terms of all finite modes, 1 suffices. All we need to do is make sure that the L2 norm goes to 0. So in particular, this automatically tells us that majority is not noise sensitive, because 1 over square root of n sums up to a constant, whereas tribes is noise sensitive, because log n over n squared gives us something that it absolutely does not sum up to a constant. This is again BKS. That same paper also proves that if you take Bernoulli percolation on a square lattice, so let's say crossing a square, that is noise sensitive in the square lattice. Now notice that this is actually not, once we have this theorem, all that tells us is that we have to control the probabilities of pivotality. And if we think about it, at least on a square lattice on the bulk, we take a point and we ask what's the probability that it's pivotal. That's equivalent to having 4 arms. 2 primal connecting left to right, and 2 dual connecting top to bottom, because this event is exactly pivotality. So modulo a lot of work about the boundaries and things like that. If we can prove that the probability of such an event to length n if we can get that this is at least n to the minus 1 plus epsilon, then we actually get noise sensitivity by that theorem, because there's n squared bits, you sum their squares up, you actually, and you actually get that this is not only small but polynomially small. Now, this is known in a lot of different ways. I'm sort of looking at the time and I think I might, yeah. So what I think I'm going to do is I want to try to prove this next week, at least try to get this bound. I'm not sure if that's realistic in terms of time, but this is actually known. For the triangular lattice, at least, we know the 4-arm exponent explicitly by SLE computations. So it's possible to actually know what the exact value is here, and I believe it's negative 7/4. I know I keep looking at you, I don't know why. Do you remember? 5/4. 548 is 1 arm. We're looking at 4 arm, it's a different exponent. Yeah. 5/4 sounds correct. So this is actually, at least for the square lattice, it's conjectured to be 5/4. It's known for the triangular lattice. And then, but there are proofs that get the 1 plus epsilon here. It's been known for a very, very long time, since the 80s. But BKS specifically has a different proof, which might be a bit of a digression. I'm not certain if we're going to have time to do it. But this theorem I do want to prove for you, at least in a subcase, which is if this is going to 0 polynomially fast in Mn. So if I, instead of saying this is just going to 0, if I give you an upper bound of 1 over Mn to an ep to some delta, then I'm going to prove that theorem to you in next week. So before we stop, let's just sort of see what this tells us about influence now. Because we now have influence appearing in 3 different norms in 3 different capacities. So the L1 norm is sharp threshold. The L2 norm is now noise sensitivity. And we have this L infinity norm lying around weirdly, sort of talking about the maximal influence through duality. So what we know is that, first of all, if the L infinity norm is constant, we're definitely not noise sensitive. No way around. At least one of these influences would be large, and we're not noise sensitive. We also don't know if we're sharp or not sharp. You always have the case of dictator to consider, which has none of these properties. No sharp threshold, no noise sensitivity, nothing nice. The second L infinity norm goes to 0. KKL tells us that we have a sharp threshold of order at least log of 1 over the rate of vanishing. That, of course, doesn't tell us anything about noise sensitivity, because this is an L2 norm. And it's very easy to construct things that have infinite L1 norm, but finite L2 norms. Majority, for example, 1 over square root of n. The one thing I mentioned shortly before is what happens if the influences are small. So given all this stuff is what happens when influences are large. When influences are small, we really are very, very restricted. And the theorem that characterizes this is Friedguth's Hutta theorem, as I mentioned before. Let me state it formally. So if I have bounded influence, then I can come up with this function q, which it's epsilon close in this sense, that the number of bits, the proportion of the bits that they don't agree on is arbitrarily small, and it only depends on a fixed number. Now, if given k, we can get a bound like c times k to the k over epsilon. So obviously the smaller epsilon is, the more difficult it becomes, and the larger k, the more difficult this becomes. But if you think of k as a fixed number, this is again a fixed number. So that, yeah.
In particular, it's not stable, but you have a weaker condition, like weaker than bounded, to get non stable on the influences.
I mean, this is an if and only if. For monotone functions, at least, it's an if and only if, so you can't hope to get better. But bounded influence functions aren't necessarily depending on exactly 5 guys, but at least they're really close to it. If I tell you that I don't have a large influence, I really need to find, this is why it's called a junta, sort of a ruling class that's finite size. So it's not necessarily 2 people deciding, but really everyone decides and the rest of the people can get an epsilon of the opinion at best. So these are very much, obviously these don't have sharp thresholds, they don't have noise sensitivity, they don't have anything. Right? Because you really are talking about a finite number of guys that you can miss with any perturbation that's going to 0. So this is a very, very stark dichotomy between functions with sharp thresholds, maybe not full noise sensitivity, but definitely infinite derivative at that boundary as epsilon goes to 0, versus very nicely well-behaved functions. Okay, I don't really have anything else I can do that's in 7 minutes. So I guess the preview for next week will be the proof of these 2 theorems. The noise sensitivity, KKL, and noise sensitivity. And the thing that's the sort of the star of this guy is going to be the noise operator. We're going to just work with this noise operator, look at the spectral sample, and use what seems like a miraculous inequality called Bonamy-Beckner, which the Bonamy-Beckner hypercontractivity, which is a very large word for a very, very stupid inequality, which is perfectly technical and completely miraculous, in the sense that it allows us to control an L2 norm with a smaller norm. That is, I'm going to take functions that have finite variance and control their finite variance with their 1.5/4 moment, for example, which of course you can't do in general, but for Boolean functions on the Hamming cube, we somehow can, and we can actually get a lot of juice out of that very technical looking inequality. Okay, thank you guys. See you next week.